Coming up on Energy Switch, ideas to decarbonize two of our most important industries.
We produce about 4 billion tons of cement per year and about 2 billion tons of steel per year. Cement is actually a pretty energy efficient material to make. The reason why it's a problem for climate change is because we're making so much of it.
Modern steel has a lot of properties that are really useful to us. It's strong, it's malleable. It is basically one of the building blocks of all the infrastructure that we have in the world today.
Next on Energy Switch, decarbonizing the cement and steel industries.
Funding for Energy Switch was provided in part by the University of Texas at Austin, leading research in energy and the environment for a better tomorrow. What starts here changes the world.
I'm Scott Tinker, and I'm an energy scientist. I work in the field, lead research, speak around the world, write articles, and make films about energy. This show brings together leading experts on vital topics in energy and climate. They may have different perspectives, but my goal is to learn and illuminate and bring diverging views together towards solutions. Welcome to the Energy Switch. We often hear about moving to solar and wind to decarbonize our energy system. But those only generate electricity, which today is just 20% of total energy. Cement and steel have created the modern world. They make our buildings, roads, machines, and products. These two industries emit nearly as much CO2 as our entire electricity system, but they're difficult to decarbonize. We'll talk about challenges and potential solutions to do this with Rebecca Dell. She's the Senior Director for Industry at the ClimateWorks Foundation, formerly at the U.S. Department of Energy and the Scripps Oceanographic Institute. Samantha Gross is Director of the Energy Security and Climate Initiative at Brookings Institute, and formerly the Director of the Office of Climate and Clean Energy at the DOE. Next on Energy Switch, part one of our deep dive into decarbonizing industry. All right, well, let's start right in. Welcome. I'm really glad you're both here with us today. You know, why is it hard to decarbonize industry? Why is that harder than everything else?
That's a great question, and one actually that I get asked really frequently. And my answer is, it's not. The difference is, we have been working for 30 years or more on electric cars and solar power and wind power and energy efficiency. And so the point is not that it's somehow inherently harder than other parts of the economy. The point is that we're farther behind.
Right.
We've made less progress because we've done less work.
Yeah. Anything to add to that, Samantha?
I would add that it's not just from using fuels. There are places, particularly in the steel and the cement industries, where we're emitting CO2 not because of fuel use, but as part of the chemistry of the process. And so that's a little wrinkle that adds a layer of difficulty.
Right.
We produce about 4 billion tons of cement per year and about 2 billion tons of steel per year. So that works out to be about 1,200 pounds of cement per person per year.
On the planet?
For every human being on the planet. And about half that, so about 600 pounds of steel per person per year for every single person on the planet.
Yeah.
Cement is actually a pretty energy efficient material to make and a pretty greenhouse gas efficient material to make. The reason why it's a problem for climate change is because we're making so much of it.
Yeah.
And so just those two materials are responsible for about 15% of all greenhouse gas emissions.
Yeah.
Just steel and cement.
Yeah, cement is, by volume, the largest human-produced product.
No kidding, 1,200 pounds.
Yeah.
I sometimes think about it as like every year there's like 4 or 5 times me made out of steel.
Right.
Globally.
Yeah, just like
It's
two
like-
of me.
It's like you can imagine these, all these other steel people following you around and accumulating year after year.
Year after year. Oh, I love the visual on that.
Well, let's dive into some of these.
Yeah.
Get started with cement. Why is it so important? Why don't we use something else besides cement?
I mean, we've been using the same process for a couple hundred years to make cement, and it's really a proven product to make something that we need. Everything from skyscrapers to highways to my little casita in Mexico is made of cement.
Right.
And so changing that has proved to be a challenge.
Yeah.
I would just say there's a couple of wonderful characteristics of cement that I would highlight. The first one is that it's basically a liquid, and you can pour it into any shape you want, and it turns into a rock.
Right.
That's great.
Right.
The other thing is that it is cheap and available. So the basic raw materials that we use to make cement are some of the most common types of rock in the world.
Yeah.
It's basically limestone.
Yeah. Affordable and reliable and available drives so many things. What's the process for making cement, and why does that emit CO2?
So the way that you make cement is you take limestone and you heat it to high temperatures, which basically takes that calcium carbonate and turns it into calcium oxide. The difference between those two substances is a molecule of CO2. And so when you think about where you get greenhouse gases from making cement, they come from two different areas. One is from burning a fuel to achieve that very high heat to make that reaction happen.
How much heat does it take?
You're up around 1,000, 1,200 degrees. It's pretty hot.
Fahrenheit or centigrade?
That's centigrade.
Centigrade.
Yeah.
Wow.
Yeah, and one of the tricky things about achieving temperatures that high is that you generally have to burn something.
And the limestone itself, when you melt it, releases some CO2, so it's a double whammy.
Exactly. So it is,
Okay.
at least the way it's operating today, it's
Okay.
a double whammy, and that you're getting it from burning the fuel, and you're also getting it from the chemistry of the process.
Anything to add to the process?
Absolutely. I think big picture, making cement requires a lot of energy, but even if we used completely clean energy, no greenhouse gas emissions energy, we would still have the CO2 that's coming straight out of the rocks.
Right.
And so when we think about solutions for the cement industry, which is responsible for more CO2 than every car combined everywhere in the world, we have to solve both of those problems. We have to solve the problem of the energy and also that CO2 that's literally coming straight out of the rocks.
Gotcha. What proportion of the CO2 comes from the melting of the limestone, and what proportion comes from the fuels?
It's a little bit more than half comes
Okay.
out of the rocks, a little bit less than half comes from the fuel
Okay.
in a modern, well-run cement kiln.
Gotcha. So what can we do to make the process emit less?
Well, you can see a couple of sort of clear options. One of them is change the process.
Yeah.
And the other is to capture and either store or use that CO2. Those are sort of the two flavors that solutions come in.
Let's start with the second one. So you capture that CO2 that's emitted from melting the limestone and do something with it, put it away,
Yeah.
store it
Yeah.
back in
store it.
rocks.
Yeah, store it underground,
You're right.
basically. Put it back in the rocks where it
Okay.
came from.
Okay.
Exactly.
Anything else to the process to emit less?
So there's one ingredient in cement, which is called clinker, and almost all the greenhouse gases are associated with making the clinker. So we sometimes talk about this as let's use cement with less clinker, then let's use concrete with less cement, then let's build structures with less concrete. And we can introduce efficiency at every level.
Gotcha.
And you add those things together, and you can get really big savings.
What's clinker?
Clinker is basically just what comes straight out of a cement kiln. It comes out as like little pebbles that you have to grind up. The reason it's called clinker is because the pebbles make clinking
Yeah,
noises
I've heard it.
when they knock together.
Yeah.
But the most traditional cements, 95% clinker. We can use other materials that have very low greenhouse gas emissions associated with them and blend those in,
Right.
use only 50% clinker, and reduce the greenhouse gas emissions for the total cement product by 30 or 40%.
Yeah. More expensive, less efficient, just
Many
as
of
good?
them are actually cheaper.
Really? Okay.
And many of them are performance improving.
So we just haven't done it yet.
That's the thing that we should just do tomorrow.
Okay.
There's no reason to wait. But one of the reasons why people haven't done them yet is that best and worst part about cement, it's incredibly cheap.
Yeah.
For a typical building project in the United States, less than 0.5% of the cost of the building project is buying the cement.
Wow.
When the cement is that cheap, you have just no incentive at all to use it efficiently.
Change is hard.
Change is hard, but
true.
important.
Yeah.
One thing that we see as like a big opportunity is that there's, here in the United States, in every state, there's one customer that basically gets to dictate the terms of the local cement market.
Oh.
And that's the State Department of Transportation.
Oh.
Because
roads.
when they build roads, they buy more cement than anybody else by a huge margin. And so if the State Department of Transportation says, hey, we want this alternative blend, then it becomes available for everybody.
All right. Can we capture it?
I think the capture will be really important in this industry because as part of the chemistry, you can't avoid that CO2 molecule happening.
Right.
And I think this is one of those examples. I think we sometimes think of carbon capture as a way of avoiding doing the other things that we need to do. But it's not always that.
Right.
Carbon capture is a way of doing things that are very difficult to do any other way.
Right.
There are places where carbon capture makes a ton of sense because there are emissions that are difficult to avoid any other way.
Yeah, yeah. Any other challenges you see on the capture side? I mean, it's full disclosure. I've had a carbon capture group for 24 years. It's still expensive.
Yeah, I would say that no one has demonstrated the system in actual practice.
Right.
So we don't have a lot of information about what percentage of the carbon is actually going to get captured.
From cement.
From cement.
Okay.
Also, if you're continuing to burn fossil fuels in your cement plant, you have all of the potential upstream emissions of extracting and transporting those fossil fuels, whether that's methane that gets off-gassed from a coal mine or leaks out of a gas pipeline. Those are still greenhouse gases. We need to count those as well.
I know this is probably hard to generalize, but how much cost would that add? And since it's only 0.5% of the cost of the building, would it, okay, maybe it adds a little bit of cost, or is it a lot of cost?
It's very difficult to estimate the costs of something that hasn't been done before.
Right.
When we talk about concrete and steel and petrochemicals, something to remember about all these industries is that they are quite competitive. They're very capital intensive.
Right.
And they're also quite low margin. And so it's one thing to say, yeah, concrete is only 0.5% of the cost of the building. We can afford this. And for the builder of the building, yeah, that makes sense. But for the concrete manufacturer, they need the whole industry to do this. Otherwise, because the industry is competitive and low margin, they get out-competed.
Right.
And so there's a couple different ways you can approach that. You could mandate it. You could put a cost on carbon such that this became the economic thing to do. But it's not going to happen without some sort of push, either a policy push to make folks do it or a demand pull by buyers saying, I only want to buy cement where you have done all these low carbon processes or whether you've captured the carbon. It has to come from one direction or the other.
Yeah.
There are incentives that are available in the Inflation Reduction Act to help cement companies start deploying these technologies. There's both kind of cash grants that are available for innovative new technologies. And then there's also a tax credit that you can get for each ton of CO2 that you capture and store.
Okay.
It's important, though, you don't get the tax credit for capturing the CO2. You get the tax credit for storing the CO2.
Yeah.
And that's another important barrier.
Yeah, that's interesting.
Developing that infrastructure is an extremely important part of getting carbon capture going, not just in the cement industry, but in all industries.
Right.
And you're starting to see now states getting the ability to regulate the injection wells for CO2. You're starting to see CO2 pipelines come up for permitting, and we're beginning to see decisions on those. But like most kinds of infrastructure, it's difficult.
It is.
But this is just getting started.
Yeah.
One thing I just wanted to put out is that there also are some new companies that are looking at ways to make traditional cement without the process emissions. And so you're a geologist, you know well. It's easy to get calcium out of limestone, but there's calcium in lots of other types of rocks too.
Yes.
Basalts, things like that.
Yeah.
And you can make a chemically identical cement without any process emissions,
Yeah.
so only energy emissions. It's
Other
a pre-commercial technology, but it's a
Yeah.
potentially
Yeah.
really exciting one if it can come to scale quickly.
Sure.
Yeah, because if it's not a carbonate, it doesn't contain that molecule of CO2 that you're baking off.
So moving into steel.
Steel, particularly modern steel, has a lot of properties that are really useful to
Right.
us. It's strong, it's malleable. It is basically one of the building blocks of all the infrastructure that we have in the world
Right.
today.
And it's tough to replace it with other things. I mean, what are our options?
I mean, we have other structural materials.
Yeah.
So we can use cement instead of steel in buildings.
Right.
That has its own problems. We can also use wood instead of steel in buildings. Again, that has its own problems. We can use other metals instead of steel for other uses. For example, many cars in the United States use at least some aluminum in places where they previously
Right.
might have used steel. The problem is that the greenhouse gas emissions associated with making aluminum can be up to 10 times higher than the greenhouse gas emissions associated with making steel. So in terms of replacing it at scale, there isn't really an
Pretty
alternative.
tough.
We can definitely use it more efficiently, but we can't get rid of it.
Right. As in so many cases, the good intentions are here, and then there's these unintended consequences, which you all are great at thinking through ahead of time, luckily for us. How does the process of making steel, where's the CO2 come from in that process?
So you start with iron ore, which is a rock that contains iron chemically bonded to oxygen. And so the main process of making steel, the thing that requires the most energy and emits the most greenhouse gases, is separating those oxygen atoms from those iron atoms and converting your iron ore into metallic iron.
Okay.
And so the way that we do that is we provide the oxygen atoms with a place they would rather go. And that is a carbon atom. So we take coal, which is basically pure carbon, and we burn some of it to create a high temperature inside our reactor. And then we use some of it to pull those oxygen atoms off the iron. And so we get CO2 from burning the coal, and we get also CO2 from that chemical reaction with the iron ore.
Okay.
It also leads into a good way to think about how to change the process.
Right.
Because we talk about finding a suitable partner. That suitable partner right now is carbon from coal, whereas another suitable partner for oxygen is hydrogen.
A third option is if you're willing to put in a lot of electricity, you can pair that oxygen with another oxygen. Then your waste product is just oxygen gas.
Interesting.
That takes a lot of electricity.
How hot is this process? I don't think you mentioned that. Maybe I missed it.
So the most common way is that we do it in a device called a blast furnace.
Okay.
And a blast furnace operates at about 3,000 degrees Fahrenheit.
3,000 degrees Fahrenheit.
Yeah, about 2,000 degrees
2,000
Celsius.
C. Okay, even more than cement.
It's very,
Okay.
very hot in a blast furnace.
Okay.
Just to kind of give people a sense of the scale here, a totally normal steel mill might produce 3 million tons of steel per year. Fully electrifying that facility would take something like 3 gigawatts of electricity.
3 gigs.
To give the audience a sense of comparison,
Right.
a nuclear power station is usually about 1 gig.
1 gig. The big ones.
Yeah,
Yeah.
so we're talking about 3 nuclear power stations to power 1 steel mill. When we call these industries energy intensive, we are not kidding.
Yeah. You mentioned hydrogen, Samantha. Are there any steel plants using hydrogen today in that substitution, or?
There are a couple of pilot plants in Europe.
All right.
But it is definitely an interesting technology because it has the potential to replace both of those parts. You can burn the hydrogen in order to achieve the temperatures you need, and the hydrogen provides that dance partner for
Right.
the oxygen that you need. The trick with the hydrogen is that it does have to come from somewhere. And so in order for this process to make any sense from a greenhouse gas perspective, you have to pay a lot of attention for where that hydrogen comes from. It needs to be produced in a greenhouse gas efficient way.
Right. So you mentioned a case, Rebecca, where electricity was being used to make steel. Is that the main mechanism for doing that, or can electricity be substituted in other ways?
Yeah, so similarly with cement, nobody has put a lot of effort into commercializing that technology until very recently, because electricity is more expensive than coal. Mm-hmm. And so people are just starting to commercialize what's called direct electrolysis steelmaking. But right now that is still a pre-commercial technology.
Right.
The process that we would use for hydrogen is actually pretty similar to the process that we currently already use to make steel using methane.
Oh, interesting.
We like hydrogen because basically we know it will work. Mm-hmm. But if we can get this direct electrolysis technology commercialized quickly,
right,
that will probably be a much more energy efficient technology.
Gotcha. I mean, how much does that affect steel's cost, something like that?
I saw a figure recently,
Yeah,
and it talked about the cost of using at least today's available green steel, like in the cost of an automobile, for instance. And they said that it would increase the cost of the car by like 0.2%.
The car?
The car.
So the end use of the steel.
The end use of the steel. So we're
Yeah,
kind of
the
back
cement.
to we're kind of back to the cement case.
Right.
Is steel a big portion of the cost of your automobile? No. Mm-hmm. But from the point of view of the steel manufacturer, it's an incredibly low margin competitive industry.
Gotcha. Who makes, just general terms, the steel today in the world?
So about half of all the steel in the world is made in China.
Okay.
And then after that comes Japan, the United States, the European Union, South Korea are the big steel producers.
Gotcha.
One side about sort of Chinese production versus production in like the EU and here in the States, for instance, is the amount of recycled steel. And that is today a process that runs entirely on electricity.
Okay.
The steel is melted in electric arc furnaces and reformed.
And it can compete on price with new steel?
Absolutely. It's less expensive.
Oh, wow. I'm glad to know that. 'Cause quite often recycling is just more expensive, so we don't do it.
Yeah, there's certain materials for where it makes a ton of sense, and steel is one of them.
Okay.
Aluminum is another.
Steel is the most recycled material in the world. Here in the United States, about 85% of steel is recycled at the end of its life.
You're right. No quality loss?
There is quality loss. And so we typically use recycled steel for lower quality applications, like rebar.
Yeah.
And then we use the new steel, the steel that's made from iron ore, for higher quality applications, like cars.
Yeah.
But there isn't a clean separation between high quality and low quality. And so you can just mix together however much recycled steel or new steel you need to meet your particular quality specification.
And integrity standards are testable after the steel is made.
Absolutely.
So you don't end up with something you didn't want.
Absolutely,
accidentally.
absolutely.
Okay.
The United States is actually a world leader in producing high quality, high recycled content steels.
Yes,
I love that.
Absolutely.
I love that.
Yeah. It's not that the Chinese don't recycle steel. It's the point where they are in their development cycle. They're still building a ton of stuff, and they haven't scrapped enough steel to have the kind of recycling industry that we have.
Yeah.
That's a neat explanation.
Yeah.
Because otherwise you end up judging.
Absolutely. And I think when we say that this huge amount of greenhouse gases, like a third of greenhouse gases, come from making physical stuff, it's easy to say, oh, well, why don't we just consume less? And here in the United States, that's probably a good idea. Mm-hmm. But the real drivers of what has caused the increase in those greenhouse gas emissions in the last 10 or 20 years is hundreds of millions of people, many of them, but certainly not all of them, in China, moving from lives of abject poverty to lives that we would consider modern, dignified, safe. And those things require huge amounts of steel and cement and other basic materials. And so we need ways to make those materials cleanly.
Absolutely.
Thank you so much for making that point so well. I wanted to make sure that came out in this conversation.
Really appreciate sharing that with us. Let's take a break. We make 6 billion tons of cement and steel a year, which makes 15% of total greenhouse gas emissions. For cement, burning the fuel to heat the limestone produces CO2, as does the chemical process of turning limestone into cement. We could use a non-carbon fuel like hydrogen, but today making hydrogen also makes CO2. More immediate reductions could come through efficiency, using less cement in concrete and less concrete in our buildings. Steelmaking also emits CO2 from the fuel and the chemical process. Switching from coal to hydrogen or electricity are potential options, but getting enough heat from electricity is hard. Steel and cement are low-margin industries, and new processes would be costly. So likely, they'd require government support initially, perhaps through procurement. Federal and state governments are the largest consumers of cement and steel. If they required lower carbon and taxpayers agreed to pay more for it, the industry could accommodate.
Funding for Energy Switch was provided in part by the University of Texas at Austin, leading research in energy and the environment for a better tomorrow. What starts here changes the world.